Hello everyone, my name is Binita Yumlambam, MTech second semester from Department of Food Engineering and Technology, Tezpur University. Today I'm going to present on the topic Pulse Electric Field Processing applied in food processing. So now let's get started. So these are the contents that we will focus on throughout this presentation. Pulse electric field technology and its principle. What is this pulse electric field technology? It is one of the emerging non-thermal food preservation methods that involves the use of short electrical pulses for microbial inactivation while imposing minimal detrimental influence on the food quality. Earlier, electroporation of cell membranes has been used in biotechnological field for infusion of foreign DNA into the cell. In 1925, Betty and Lewis used non-pulse electric field of 220 volt to pasteurize milk and found reduction in microbial load. PEF has a wide range of applications ranging from liquid or semi-solid foods to solid foods. A pulse is a single disturbance that moves through a medium from one point to another. In PEF technology, it involves the use of pulses having higher electric fields for only a few micro to milliseconds with intensity in the range of 10 to 80 kilovolt per centimeter. PEF uses short high voltage pulses to liquids or semi-solid foods placed between two electrodes to preserve the foods. The applied voltage ruptures the microbial cell membrane and inactivates endogenous enzymes at or near room temperatures. During treatment, the food material is in close contact with the electrodes and hence is subjected to an electric field. The average electric field strength E is as follows: E equal to V by D, where V is the voltage across food samples and D is the distance between the electrodes. Applications of PEF are primarily focused on pathogenic and spoilage-causing microorganisms in food. In addition to this effect of controlling microorganisms, it delivers shelf-life extension without using heat treatment and preservation of sensorial and nutritional qualities of food. It has been applied in products such as milk, milk products, egg products, juice, and other liquid food products. The benefit is that it provides pasteurization effect and results in better retention of nutritional and sensorial qualities than conventional thermal pasteurization. The pulse electric currents are transferred to the sample placed between a set of electrodes inside a chamber, usually at room temperature. The distance between electrode is termed as the treatment gap of the PEF chamber. Food sample is capable of transferring electricity due to the presence of several ions. The electric field applied may be in the form of exponential decaying, square wave, bipolar, or oscillatory pulse at ambient or subambient or slightly above ambient temperature. PEF treatment is restricted to food products with no air bubbles. The figure shows the flowchart of pulse electric field processing in food. In PEF processing system, it mainly consists of high voltage pulse generator, treatment chamber, and a control system for monitoring the process parameters. High voltage pulse generator provides electrical pulses of desired voltage, shape, and duration, and the treatment chamber consists of two electrodes with an insulating region in between where the treatment of the product takes place. One electrode connected to the voltage source and the another to the ground. PEF treatment system. The main components required for a pulse electric field application are an impulse generation system and a treatment chamber. A crucial prerequisite for an economic and efficient production is continuous operability with high flow rate capacity, which led to the development of continuous treatment chambers where the food is pumped through while being exposed to the electric field at ambient or refrigerated as well as elevated temperatures. Before treatment, heat exchangers might be used to preheat the media, and after the treatment, the dissipated electrical energy resulting in a temperature increase has to be removed before aseptic packaging. One of the main advantages of PEF treatment is its continuous operability with very short processing times. Therefore, a system can easily be implemented into existing processing lines. Generation of pulse electric fields. The impulse generation system transforms the electric power from a low utility level voltage to pulse high intensity electric fields. A simplified circuit for generation of exponential decay pulses is shown in figure, consisting of a charging and a discharging unit. In the first one, an energy storage device is charged across a charging resistor by a DC high voltage power supply. The generation of pulse electric fields requires slow charging and fast discharging of the energy, as the pulse weight is short in comparison to the time between pulses. The charging voltage U0 required to generate pulses of sufficient electric field strength is highly dependent on the electrode distance. For two parallel plate electrodes, the electric field strength E is given by E equal to U upon D, where U is the voltage in kilovolt and D meter the gap between the electrodes. Dependent on the type of switch and the configuration of the discharge circuit, several pulse waveforms are possible, but two have mainly been used. They are the exponential decay and square wave pulses. And the treatment chamber design. The treatment chamber wherein the food is exposed to the electric field pulses consists of at least two electrodes, one on high voltage and the other on ground potential, separated by insulating material in different geometric configurations. Here, the figure shows the different types of treatment chamber designs. The first one is the parallel plates, second is the coaxial, and the third one is the collinear cylinders. They have been commonly used in the food processing. Main processing parameters. First one is the electric field strength. Pore formation will occur when a certain threshold value of the transmembrane potential form is exceeded, which was found to be in the range of 1 volt. It was shown that the critical external field strength is highly dependent on cell size as well as cell orientation in the field. A critical electric field strength was found, which was dependent on the size and geometry of a cell in the range of 1 to 2 kilovolt per centimeter for plant cells and 10 to 14 kilovolt per centimeter for microbial cells such as E. coli. And the second one is the treatment time, specific energy, and pulse geometry. Apart from the peak electric field strength, the product of the pulse width and the average number of pulses applied has often been used to evaluate treatment intensity. Increasing treatment time results in higher microbial inactivation. The pulse width is defined as the time where the peak field is maintained for square wave pulses or the time until decay to 37% for exponential decay pulses. And the third is the treatment temperature. Treatment temperature has a highly synergetic effect on treatment efficacy as it has a significant influence on cell membrane fluidity and stability, whereas at low temperatures, the phospholipid structure is packed in a gel-like structure. Their order decreases with increasing temperature. The fourth one is the treatment medium factors. The treatment medium factors, it includes conductivity, effect of air bubbles and particles, and cell characteristics. In the conductivity, media rich in ionic species such as tomato juice present problems in achieving a significant voltage for a supercritical field strength, since a smaller peak field strength is generated across the treatment chamber. And the effect of air bubbles and particles. Air bubbles, which cannot withstand high electric field strengths, may be present in the case of sparkling products or be released due to temperature increase or electrochemical reactions. In particular, for microbial inactivation, where an electric field strength in a range of 30 to 50 kilovolt per centimeter is required, air has to be removed from the product. Apart from dielectric breakthrough, where a high current will flow within a narrow channel within the bubble instead of the liquid, the different dielectric properties of air will influence treatment efficacy. A similar effect has been found when agglomerations of microorganisms and or particles with different dielectric properties such as fat globules are present. And the cell characteristics. In general, gram-positive organisms seem to be less sensitive than the gram-negative organisms. Mechanisms of action. The primary effect of PEF on biological cells is related to local structural changes and the breakdown of T cell membrane. Two mechanisms are proposed for the mode of action of pulse electric field action on the microbial membrane of the organism. The first is the electroporation, in which the cell is exposed to high voltage electric field pulses that temporarily destabilize the lipid bilayer and proteins of the cell membranes. And the second is the electric breakdown, electromechanical instability theory. The cell membrane is considered as a capacitor filled with dielectric material of low electrical conductance and a dielectric constant in the range of 2. Accumulation of charges with opposite polarity on both sides of the membrane leads to a naturally occurring perpendicular transmembrane potential of about 10 millivolt. By exposure to an external electrical field, an additional potential is induced by movement of charges along the electric field lines, resulting in a viscoelastic deformation of the cell membrane. When the overall potential exceeds a critical value of about 1 volt, depending upon the compressibility, the permittivity, and the initial thickness of the membrane, the electrocompressive force causes a local dielectric rupture of the membrane, inducing the formation of a pore acting as a conductive channel. The electric breakdown is reversible if the pores induced are small in comparison to the membrane area. Increase of electric field strength and the treatment intensity by increasing pulse width and or number will promote formation of large pores, and the reversible damage will turn into the irreversible breakdown associated with mechanical destruction of the cell membrane and cell death. A critical electric field strength was found, which was dependent on the size and geometry of a cell, in the range of 1 to 2 kV per centimeter for plant cells and 10 to 14 kV per centimeter for microbial cells such as E. coli. Effect of PEF on microbial inactivation. PEF inactivates vegetative cells of bacteria, molds, and yeast in various foods. Yeasts are more sensitive than bacteria. Also, gram-positive bacteria are more resistant than gram-negative bacteria. The application mainly focuses on foodborne pathogens and spoilage microorganisms. Various factors influencing the microbial inactivation are intensity of the electric field, pulse width, safe, conductivity of the medium, pH, energy input, treatment, temperature and time, type of microorganism and its growth stage. Induced transmembrane potential is directly related with size of cells. Yeast cells possess greater resistance than bacteria due to bigger size of yeast cells. The sensitivity also depends on the growth stage of microorganisms. The organisms are more susceptible during log phase, whereas they are resistant in stationary phase. Decrease in the pH and increase in temperature have synergistic effect on microbial inactivation during PEF treatment. Presence of fat globules, agglomeration of microorganisms, and presence of air bubble in product are other few factors affecting the microbial inactivation. Effect of PEF on enzymes. For the inactivation of enzymes, it requires more stronger electric field than microbial inactivation. Pulse electric treatment at 21.5 kV per centimeter and high energy input reduced the lipase and peroxidase activity of raw milk by 65% and 25% respectively, with negligible effect on alkaline phosphatase activity. Whereas at the same treatment condition, peroxidase and polyphenol oxidase showed a moderate reduction in activity of 30 to 40%, and alkaline phosphatase showed only 5% reduction in its activity. Complete inactivation of peroxidase was observed in PEF treatment watermelon juice than heat-treated juice. A study on PEF treatment of papain showed irreversible reduction of enzyme activity. The papain activity was not recovered after 24 hours storage at 4 degrees Celsius. The reduction in activity of papain is due to the loss of alpha helix structure in papain molecules. Effect of PEF on food quality. When treated orange juice with PEF and compared with thermal pasteurization at 94.6 degrees Celsius for 30 seconds, PEF treated juice retained higher amount of vitamin C and flavor compounds than conventionally pasteurized sample. In case of flavor components such as decanol was found to be reduced by 40% during thermal pasteurization, while no such loss was observed by PEF treatment at 30 kV kilovolt per centimeter, either at 240 or 480 microsecond. It has been reported that even if some compounds suffered losses during PEF treatment, it will always be in less proportion than the heat pasteurized juice. PEF treated orange carrot juice 25 kilovolt per centimeter for 280 microsecond and 330 microsecond was compared with heat treated juice at 98 degrees Celsius for 21 seconds. The shelf life and ascorbic acid degradation rate of both the samples were investigated. It was observed that the ascorbic acid in the heat-treated orange carrot juice was 83%, whereas in the PEF-treated juice it was 90%. PEF-treated orange juice extended the half-life of the juice stored at 2 degrees Celsius to 50 days compared to heat-treated juice. High-intensity PEF-treated watermelon juice maintained brighter red color than the heat-treated juice throughout the storage time. Applications of PEF. PEF in food processing. In food processing, PEF has roles in pasteurization, drying, and extraction. In pasteurization, PEF processing has promising applications in pasteurizing many variety of liquid and semi-solid foods, with special reference to the inactivation of microorganisms and prevention of developing off flavors during storage. Several spoilage causing and pathogenic bacteria, particularly E. coli, Listeria, and Pseudomonas species were inactivated with increased electric field and time. In PEF-treated milk, the nutritional quality of milk remained unchanged with no loss of vitamin B1 and vitamin B2, vitamin D and vitamin E, but vitamin C showed 93% retention. In 1996, Food and Drug Administration (FDA) approved the use of PEF in the preservation of liquid eggs, while the first commercial PEF application for fruit juice preservation was installed in the United States in 2005. In drying, due to the opening effect of cells, this technology can be used to facilitate rapid removal of moisture from cell matrix. Thus, it finds its application to enhance chemical reaction and drying process. The principle of permeabilization is successfully used to enhance mass and heat transfer to assist drying of plant tissues. PEF technique has been applied as a pre-treatment before osmotic dehydration of carrots. The samples were exposed to different levels of exponential pulses with a total specific energy input in the range of 0.04 to 2.25 kJ per kg. The electric field strength was in the range between 0.22 to 16 kV per centimeter and pulse duration between 378 microsecond and 405 microsecond. The PEF treated carrot samples were further treated with sucrose solution 50-degree brix at 40 degrees Celsius for 5 hours, and the results were compared with untreated osmotically dehydrated samples. It was observed that PEF-treated samples showed reduced moisture content and increased solid content during osmotic dehydration. And in extraction, the PEF technology can also be applied for the disintegration of biological tissues that enhance the extraction of intracellular compounds from different fruits. For example, pectin can be extracted traditionally through enzymatic reaction, but this reaction has less yield of pectin due to poor efficiency. Alternatively, PEF treatment is employed as short pulses to avoid excessive heat and undesirable electrolytic reactions that can enhance the extraction rate of pectin from fruit pomace. And in during oil extraction process by both pressing and solvent extraction, application of PEF at 60 pulses of 5 kV per centimeter and 120 pulses of 7 kV per centimeter, pulse duration at 30 seconds as pre-treatment increased the oil yield. The PEF treated oilseeds also showed higher concentration of tocopherols, polyphenols, and polyesterols after extraction. Higher juice yield of about 75% was observed in PEF-treated vine grapes compared to the control sample, which is 70%. Also, it increases the total anthocyanin content in grapes. Almost 3 times higher anthocyanin content was reported in PEF-treated grapes, which is applied at 3 kilovolt per centimeter at 50 pulses than that of the untreated grapes. The second application is in the waste sludge treatment. PEF also found application in reducing the solid volume or sludge of wastewater. Due to the breakdown of cell walls during PEF treatment, the cell contents are released to the surrounding. Those burst cells are much more susceptible to other biological and chemical processes such as anaerobic digestion, which can significantly reduce the solid content or sludge in wastewater treatment facilities. Another application is PEF and meat quality. PEF technology can be employed in meat processing for various purposes, including enhancement of cell permeation to increase tenderness, attenuation of microbial load to improve the shelf life, and maintenance of volatile profile of meat during storage. PEF technology can considerably improve enzyme release and glycolysis that are essential for proteolysis for meat tenderization and application in stress induction. It was shown that metabolic activity can be stimulated and extractability of intracellular compounds was improved. A PEF treatment at low temperatures does not damage enzymes or proteins, thus the potential to extract valuable components is provided. For example, mild sublethal treatment of maize germs increase oil yield and phytosterol production, resulting in plant oil with a greater phytosterol concentration. And in this integration of biological material, when applying pulse electric field to cellular tissues, an increase in mass transfer coefficients could be observed. Based on this possibility, conventional processing can be supported or replaced, as a PEF treatment allows a defined degree of tissue permeabilization. Biological systems can be stimulated in terms of metabolic activity, and the recovery of valuable components can be improved. Advantages of PEF can be discussed as follows. Pulse electric field processing almost maintains the product quality without thermal and mechanical stress. It does not degrade nutrient properties. No harmful byproducts is produced. PEF treatment increases the extraction yield. PEF allows structural modification of products. PEF as a pre-treatment before drying helps in softening vegetable tissue and improves mass transport of water. It can be integrated in production lines. It is highly suitable for extraction of secondary metabolites which are unstable at temperature and mechanical stress. And the limitations of PEF. PEF techniques are mostly suitable only for liquid foods and pastes regarding to the pasteurization. There is a need to optimize the process on solid matrices, including through the design of new contextual regarding to the permeabilization pre-extraction, high cost of initial investment, and high energy dissipation. The following points have been made as conclusion. First, the low energy consumption 1 to 2 kJ per kg for stress induction and 5 to 10 kJ per kg for plant cell permeabilization, and the continuous operability of this short-time waste-free membrane permeabilization technique are key advantages and allow the development of innovative, cost-effective, and sustainable processing concepts in the food and drink industry as well as in the biotechnology and pharmaceutical industry. An application of PEF for food preservation provides the tremendous potential to preserve high quality products at lower temperatures and short residence times to retain the fresh-like character and nutritional value of the products. A task still challenging for electro engineers is the development of equipment with reliable industrial scale generation of high strength electric field pulses. The availability of these pulse generation systems will be a prerequisite for industrial application. The uniformity of treatment intensity distribution has to be improved by optimization of treatment chamber geometry. Application of PEF in wastewater treatment, revealing its applicability to reduce the amount of excess sludge, which is an issue of the high importance considering tightened ecological measures, shows the tremendous potential of this emerging technique.